Ring, and you have the micro, Steve. Thank you.
Thank you, Francois. And Hi, everybody. It's going to be a little bit different this time because you're going to have some homework, and we'll work this out later. But there are some experiments to do. But to get started, for most of the time we've been together, we've been talking about specific objects or interpretation of specific classes of spectra. But with few exceptions, we haven't really discussed the other side of light, which is its interaction with moving media. The last time we spent together some time on the formation of images, what phase means in transfer of radiation, but we haven't really faced up to the fundamental problem that we have in astronomy, that we never have ground truth. And by that I mean, with the exception of planets where we've either sent probes into the atmosphere, as in Jupiter or Saturn, or we've had flybys in very close encounters, which is all of the planets, or where we've actually put instruments down. It's a very, very small sample of objects, and more to the point, they're not stars. The first time, and in fact, the only time we've ever had that ability to look at the sun in the same way we would look at a star is with Parker probe, which actually is the sort of ground truth, but only for the outer solar atmosphere. It's never going to be possible for us to make it to the surface or even sink something into the sun, notwithstanding science fiction films like Sunshine. So, in order to probe these media, we have to make some pretty strong assumptions, and all of these are based on remote sensing. So, it's at this point really important to talk about what happens to a photon that's stupid enough to start moving outward from the photosphere of a star. So, to begin with, in the scenario, we'll start with what an optically thick surface means, or rather, put bluntly, what do we mean when we talk about the surface of a star or any objects? But stars are very easy things to deal with in the sense that they're kind of spherical and they're big and they're blobby and they have nuclear sources and all of that. And they're pretty homogeneous on their surface, leaving aside things like sunspots and the non-uniformities, the blemishes, if you want, and leaving aside the astrodermatology. What we have when we're looking at a star is some surface from which the light is able to not freely escape to us, but pass through a medium that we'll say is more transparent. And the important thing is, and this is something we'll just keep coming back to today, the passage of light through a medium isn't just one photon going through. You have to think of radiative transfer not as waves going through a medium, but bunches of photons going through a medium. We're not talking about the classic single file group moving along in a nice ordered stream. We're talking about something more akin to a mob in front of an exit, that you're looking at you're looking at bunches. chaotic as they might be, numerous as they might be, but you're not looking at single photons. But we talk about the processes as if they are single photons. So, because of that, I have to introduce another idea which will be important for everything that we'll be doing subsequently today. And that is if you imagine having a target. So, well, let me try something. We haven't done this, I haven't done this with the whiteboard yet. So, hoping that it's actually possible to do something reasonable here. Um, Okie dokie. So here we have a pen. So you imagine that here somebody has set up a target, presumably presumably concentric, and you usually think of target practice as being here, let's say, sorry for being bellicose here, but taking, say, a single bullet and having it shot at a target and having it land somewhere in here. Okay? And then you have a bunch of bullets and you get some idea of the person's aim by looking at the distribution that they form over this surface. Okay, so far?
Yeah.
Now you imagine that what you're trying to do is predict for the average person, say the average shot here, what is going to happen if they fire at this target.
Uh,
Okay? I don't know why names are suddenly appearing on this screen. Um, let's try this. But what you could do to say, well, you know something about the way people handle a pistol by looking at the distribution that you have of positions X and here the number that you would have of hits at that distance X from the center. Okay? Again, so far?
yes.
Now, what you might see if you have some group that really doesn't know how to shoot straight, you'll say this is the center and this X is actually the radius of some annulus here. And so it's pretty clear that if you have a group of really good shooters, that center point here, so this is, we'll call it just X0 for the center, this would be the most probable that they would hit. That if you looked at a bunch of really
Ah,
good sharp, have we just lost the whiteboard?
sorry.
Okay. This is a new experience, Francois. So,
Yes, because we had mouses on your blackboard.
well,
I see Roger Hello, Hello,
okay.
Bob. I don't understand why Hugo.
Can you stop the
What
recording for,
other?
Francois, I think if you look up on the upper right corner, upper left corner, excuse me, you'll see there's a 1, 2, 3. You might be able to recover the page that he had.
no, this is fine. I'll just do it again.
Okay, and everybody else should keep their mouse quiet.
Yes,
Yes,
please.
please.
Please. So again, the point is, let's say that you have these being the distribution of hits. And now I'll be a little bit more realistic that this is, let's say, the distribution where the center is here, and we have now the number of hits at a given position. Okay? That means that in a frequencist way of talking about things, the chance of finding something at, let's say, this position is the number of those hits divided by the total number of shots.
Oh, Jesus. Come on.
Okay?
Okay.
So far?
Yes.
Okay. The reason I'm talking about this is that in a very simple way, we can then take this as a model for a shooter and say that we don't have to here
Hi.
see an individual.
Okay, I'm just listening to a lecture right now from Italy. This is part of my spectroscopy group. So kind of, yeah. What you up to?
Please,
Francois, can you stop the
yeah,
recording for a minute?
Well, yeah,
uh,
I'm going to go to a friend's just for a couple hours tomorrow evening to play some Yahtzee with some people. Yeah, I know,
where are
fun.
you?
Yeah, a wild night.
John, your mic
That'd
is
be
on.
probably from around
Francois.
6 to 10, but other than that, I got nothing
What's the
going on.
problem? Come back. Uh,
Okay.
sorry,
No, starting again.
I don't
Um,
understand.
okay. Let me do a share screen here. Remember, technology is supposed to make life simple, and of course it never does. So, um, let me use this as a better example. What I'm showing here to start with is imagining that you have, as I wrote, how to gamble with drunk photons. Let's just say instead of using the target practice, we use something much more normal, much more familiar. You have somebody who begins walking. Let's say they have a dog, okay? And you know that dogs sort of get curious about their surroundings, and so they'll kind of start and stop, but they'll also have their own idea of where they want to go and more how far they want to go. Okay? So, what you might want to do is get a distribution of the kinds of steps that your dog is going to make going ahead or to the side, and to get from that some idea of what your typical walk with the dog is going to be. Now, the example put in human terms rather than dog terms is called a random walk. That you have in, or sometimes it's called the drunkard's walk. You have you have a path where you go straight ahead, and instead of changing direction, you change how far you go on each step. But each step is independent of everything but the previous step. That is, when you go from point x1 to x2, that distance is a random variable. And the only thing it depends on is starting from whatever point you had. In other words, every time the system has no memory, it takes a step with some random magnitude. Now, if all lengths are equally probable, then you literally can't predict anything about what the next move is going to be. So you have an ensemble of equal time intervals, but random distances, which is the equivalent of saying you have different speeds if you take a constant time interval. Okay?
Okay.
Now, this is the classic dynamical picture, and you've all grown up with this because this is how we describe ideal gases, that you have a completely random process. Molecules don't see each other at large distance. If you have an ideal gas, they are neither attractive nor repulsive. They simply bounce off each other. And so if you have some ensemble of colliding particles, some are going to get more energy, some are going to get less energy or impulse in each one of the collisions. They'll change direction because they'll either be head on or they might be slightly at an angle. But when you average over the whole ensemble, each particle goes through a random walk, forgetting what happened in the previous step, other than carrying the amount of momentum that it got in the last kick. And if the process is taking place in a gas that can't lose energy, so literally the ideal gas configuration, then the ensemble has a kind of average. And that average is what we call temperature. Okay? This is just to put it in a physical context because it's actually going to be very important in a little while. Now, one of the standard distributions, again, this is something you know, is a Gaussian, otherwise called a normal or a bell curve, in which the most probable step or the most probable value is, if it's symmetric, as I've done this one, the most probable value is 0. If you can have, say, forward and backward steps, the most likely step, if it's a Gaussian distribution, is zip. Then you have a range in which it is highly probable that you're going to be sitting, and another range progressively farther away from the center where it becomes progressively less probable. Now, there are two features about this distribution. One is that if you take the total possible range of steps from minus to plus infinity, if you imagine the drunk can only go forward or backward, nothing else, then again, the most probable value, if it's equally probable to go forward or backward, will be nothing. But there'll be in time some range such that, and this probably sounds a lot like life in general, you go a few steps forward and a few steps back and a few steps back and a few steps forward, and eventually, if you look at how far you've been able to sample, you will have gone a fair distance, but you won't have ever really exited from where you are. There's no net escape in this system. Okay? This is just a standard way of looking at dynamics in a random system. But you know that when you're kind of inebriated, it's not in a one-dimensional world. Hopefully, it's only in a two-dimensional world, so there are no steps or curbs. But we'll say that you're just in a two-dimensional. So instead of walking backward or forward, you can also go right or left. Now, that changes things completely because now you have two potentially independent variables, one of which is, are you going to go some distance either ahead or backward. That doesn't matter for the moment. But we can now separate this into two variables. One is the length of the step, and the other is the direction of the step, which is going to much more closely approximate life with a dog. Okay, that you're walking along, the dog suddenly gets curious about something on your left, and whoop, you wind up going to the left, but only a small amount because it was right next to you. And then, maybe the fur ball gets a little bit curious and goes backward, and then suddenly smells something and goes ahead. Okay, I think some of you have had this experience. Now, that is a two-dimensional random walk that's referred to as Brownian motion because Brown in the 19th or very early 19th century observed the motion of pollen grains in water under ordinary conditions microscopically and noticed that there was a continual agitation no matter what level you looked at of magnification. Nothing stayed stable. And this became the basis or a basis of fundamental kinetic theory. It was what Einstein did his earliest work on in the theory of Brownian motion, and Shmukovsky and Langevin and some of the physicists that founded our business. But that's an aside, but not completely irrelevant. Because instead of imagining that it's a person who's walking, now think about what happens if you go back to what we were talking about last time with the passage of light through a medium. That in a vacuum, you know damn well that light travels at a constant phase speed, which is the same as the group velocity. It does not disperse in a vacuum. You could almost say that that's the definition of a vacuum. But it goes in a straight line, at least for the moment, okay? We're not going to get into the details of gravitational deflection and stuff like that. Just imagine now that you put some garbage in the way, but it's very tenuous garbage, otherwise called the interstellar medium. Now, the photons will continue once they've been emitted from a star or a source, they'll continue until or if they hit something. In other words, if there's some mass that has a cross section that's finite and it is along your line of sight, there's a finite probability, let me use the word chance for the moment, that the photon won't simply go past that target because that target happens to be in the way at that moment. There are then, as you know from our other discussions, two possibilities. The photon can scatter, in which case it's simply a change of direction in the simplest form, like reflecting off a mirror, or it can be absorbed. Now, that's where we come back to this concept of the random walk. In a really tenuous medium, the average step is bloody close to infinity. If you have the interstellar medium, the distance that a photon travels, and we'll get to this in a few minutes in detail, but in a stellar atmosphere or in the Earth's atmosphere, a photon will make it only a matter of meters, centimeters, or even less. The medium is going to be dense enough, even though it's tenuous enough that light can pass through it and escape to space. The mean free path before a photon interacts with matter is exceedingly small. That instead, if you look at the interstellar medium, we can see stars that are kiloparsecs away from us. A star has a radius of even a supergiant has a radius that's less than 1/100th of a parsec. So we're talking about effectively an infinite mean-free path for photons that are seen against the interstellar medium, okay, or passing through it. On the other hand, when you look at the spectrum of an O star or a B star, when you look at stars either in the ultraviolet or in the visible, you see lines that arise from the intervening medium. That is, you see lines of neutral sodium and ionized calcium, and in the ultraviolet, you see even more lines because that's where those transitions sit. But these are coming from individual interactions occurring along the line of sight with some probability. Now, in the interstellar medium, the densities are extremely low, and this is why I'm sorry that I can't show you this on. Now let's see if I can at least get the okay, let me stop screen sharing for a moment and try the whiteboard.
Okay.
Okay, we have here the stream of photons that's coming in. Okay, we'll say this is the interstellar medium. Now, a photon is going to pass through this medium, and we'll say, just for the hell of it, somewhere along the line of sight, a single photon encounters a single atom. Now, what can happen there is one of two processes. Either the photon can be absorbed, and before anything else can happen, so it comes in here, there's a resonance. This is something you know very well. It excites it. We would say, oh, it's been absorbed. But the level has a finite lifetime. And so there's a decay, in which case now, because it's this roughly the same energy, the same photon goes out. So you would think, looking here, that nothing's happened. Okay? You have an absorption, you have an emission, they balance each other. Great. The photon simply continues on its way. It has a temporary rest stop. But that's not actually what happens. And this is why the dog is the example. Because of the emission process, you would have the best analogy is with an antenna. You don't get monopole radiation. You get dipole or quadrupole or octopole. You get a pattern of radiation in which some is going to be radiated in the forward direction, if this is the direction of the incoming photon, and some is going to be radiated backward. Okay, this is what we were talking about last time with polarization and the concept of coherence. This distribution is that epsilon, that y, that angle that I talked about before in the random walk. That if you have a pure drunk and you have a pure random walk, the steps are uncorrelated, and so are the directions in which the poor person stumbles. So all directions become equally likely, and this fills the whole surface densely. But here, if you've got a dipole, this is relative to the incoming direction. So if you have a scattering event, it can cause the photon to be re-emitted. Remember, you're here. Okay? The photon, if it's simply scattered, may go this way, it may go this way, or it may come to you. But if you look at the whole distribution, the likelihood that it's going to go in the forward direction is very small. Okay? Because it's a particular angle. And so if we actually write something that's a more complicated pattern, let's say something like this, so a quadrupole, then there are angles where it's going to be more probable than others. The result is that if you have a whole bunch of photons, which is why I did this in a thick line, each one of them is going to interact with some of these atoms. But along the line of sight, those are going to be scattered. So there's a chance that when the photon is re-emitted, as it must be, if the medium is low enough density, it isn't going to be re-emitted along your line of sight. And because the probability of emission is anything less than 1 in your direction, that it's only a fraction of the total range of, in this case, 4 pi as a solid angle, you're going to see fewer photons in that direction, in that line, than in the continuum. And so you say you're seeing an absorption line, but in fact, you're simply seeing a dark line. Okay?
Uh,
The depth of the line is proportional to the number of photons that have been kicked out of your line of sight. Now, of course, you have the chance that photons that are hitting this atom are going to go into your line of sight. That's pretty damn small. So in general, because stars are pencil beams, even though they are gazillion photons in a beam, we treat the beam as if it were like a lane of traffic. In fact, the best way you can think of this isn't even in photons, but imagine that you have here a stream of traffic, and here you put up a barrier. And some of the cars are going to be scattered from the barrier, and some of them are going to go through. Okay, so you can figure out something about the size of the barrier by knowing the relative fraction that go through. In this case, the barrier is a spectral line. It has a fixed wavelength. This is what's different from atoms and molecules and dust. Dust doesn't have specific resonant absorption lines. It has bands. They're very wide and don't have the same coherent behavior. Solids behave differently than individual atoms or molecules. The reasons we can get to in another time, if you'd like. But here, there's another possibility. And this one you know from stellar atmospheres. If the medium is dense enough, then this lifetime now is challenged by the possibility that something else is going to a particle is going to zip by, and there's going to be some kind of electromagnetic interaction between these buggers. Okay, that atoms, even in the interstellar medium, are not alone. It's just they may be like living in, central New Mexico versus living in Central Park in Manhattan, that you may have the same number of people, but they're scattered over a very large area. And so the density is really low. And you don't have to worry about running into somebody. But if you're random walking in the middle of the Jemez Wilderness, and you're random walking in the middle of, say, Battery Park in New York, the probability that you're going to hit somebody is very different, or rather, that they're going to hit you. So if you imagine that what's happening in the interstellar medium is the particles are so low density that the collision time, by which we mean the perturbation, is long enough that the lifetime of the level determines what's going on and not the density of the background. And so scattering is normal in the ISM. When we see absorption lines from the interstellar medium, we are seeing lines from a medium that is as low density as we can typically imagine, a few per cubic centimeter, over distances of parsecs to kiloparsecs. The reason we can even see the damn thing is because the path length is so long. And if you have randomly distributed particles, they all have finite cross sections, no matter how small. And that gets us back to what this means. When we talk about the emission characteristic in angle, where this is called a phase function, it measures what the likelihood is that if we have radiation from an atom or molecule, it goes off in some specific direction. Okay? I
Yeah.
hope that's now clear. When looking at the individual atom or molecule, these levels, there is an intrinsic interaction strength, which we'll call the absorption coefficient or the scattering coefficient. And just so I have a symbol, absorption is usually written as a kappa and the frequency is nu, or scattering, which is a sigma. These are just conventions, but because I'm used to this, I'll fall into it in any discussion. So this will, I hope, explain it. When you say that you have an absorption coefficient, the absorption coefficient and the scattering coefficient are really essentially the same thing. It's the outcome that's different. Absorption means that after this excitation, no photon emerges. It's not that the energy is lost. It's that in the time that it takes for this to radiate, it's been perturbed. Now, I'm going to go to a new whiteboard. Amazing how slow this is. So we'll take a two-level system that, and I deliberately drew these as fuzzy. Like any oscillator or any system that has a finite lifetime, the levels of atoms and molecules have a finite dispersion in energy. That may be very, very small, or may be very, very large. That it depends on the lifetime of the level that determines just how fuzzy the level is. But this separation and the individual energies, so if this is E2 and this is E1, then the Bohr rule tells us that the separation between these determines the photon energy. So how much energy is needed to excite, and then how much will be re-emitted when it de-excites. Now, if you got a particle that comes along from somewhere, okay, now somehow, yeah, okay, so this is almost making sense. So we have a particle that comes in here and interacts just because it's a charged particle. This is the kind of thing that's easy. Then that interaction is the equivalent of giving energy to or taking energy from the system. And consequently, this lifetime changes. That energy can be withdrawn from the system. The electron that was in the excited state, if it's an atom, can then drop back with no photon being emitted. Okay? So the photon is absorbed, the system is excited, it interacts with something in the meantime, and no photon comes out. Consequently, what you see is, if you're looking at a background source, you see, sorry, you'll see that. That is, if you look from any direction, the photon doesn't reemerge. So from any direction, you see an absorption line. I hope now that's clear. That when we talk about the formation of an absorption line, it is not just an arbitrary dark line. It is the removal of a photon from your line of sight. This is very important because this is the definition of the local equilibrium condition in a gas. If we talk about the gas having a temperature and we want to, from a spectrum, from the strength of the line, we want to obtain properties of the medium. If it is only a scattering line, we can't do that. The only thing we'll be able to say with certainty, if you see scattering, is that the element or the molecule that caused that scattering is in the medium. So you can say you have iron or manganese or carbon, but you can't say how much of it you have. If, on the other hand, it's actually an absorption line in the sense that I've just said, that the de-excitation has exchanged the energy with the background gas. And if the excitation is also related to the energy of the background gas, then measuring here the total amount of light that's been removed by that line. So if this is your wavelength, the total amount of light that's been removed is proportional to how much of that element is along your line of sight. You notice the number of caveats I've put in here. That when you measure simply how much of a deficit in light you have, you're making two very strong assumptions. One, you have a medium which is in front of a luminous source. You don't know where it is a priori. You simply know that there's something there. It doesn't mean, and please keep this in mind, it does not mean that you're looking at something that has a lower temperature. You know, it's always said that when we first, in fact, teach elementary astronomy for those we want to ruin for life, we always say things like, well, if you have a hot, tenuous gas, you're going to get an emission line. And if you have a cold gas, then you're going to get an absorption line. So if you have a hot gas behind a cold gas, you're going to see an absorption. And if you have a cold gas behind a hot gas, you're going to see emission. And yeah, that's true, sort of. It works in the laboratory, but it isn't that simple. And if you're going to do astronomy and understand what it means to interpret the lines, you have to keep in mind it ain't that simple. That the only thing you know when you see a dark line is that between you and the source of that light, something was removed. Now, that said, the line profile is formed not just by the light, again, let's just to do typical cartooning. So if this is our target, then we have the photon coming in, and let's just say for the moment, it's absorbed. So we have this. Now comes the problem of the medium itself. We took, in the way that I was describing this, I took a picture of something that's static, that you simply have the atoms, if you remember the previous cartoon, they're just there, but they're moving. And this is also important because, as you know, motion relative to the source is going to produce a Doppler shift. If you're moving toward the source, the photons that are coming in are blue shifted. If you're moving away from the source, the photons are going to be red shifted. Okay? So this separation is fixed by atomic structure. If it's hydrogen or helium, this is why you can do laboratory identifications that apply to stars and and galaxies. The separation, the pattern of an atomic or molecular spectrum, the separation of the individual lines depends on the energy levels, and those are internal. But this isn't what the photon is seeing. If you have a photon here with a frequency, then what happens if this atom is moving toward the photon is that this sees, you know this from sound, okay? That when you're moving toward the source or it's moving toward you, I'll ask this, do you hear a higher or a lower pitch? That is, does the frequency go up if you're moving toward the source or down? Boy, this is just like my class. Ask a question and everybody suddenly goes silent.
We're all muted.
You're all muted. Try somebody not muting and giving an answer.
A source coming toward you, frequency is higher.
Exactly, it's blue shifted. Okay, now, if that means then that the photon frequency, because of relative motion, can be changed, then the photon that's being emitted is also going to have its frequency changed relative to an observer. So if, remembering that pattern, if the photon is scattered in one direction, it's going to be blue shifted. If it's scattered in the other direction relative to the observer, it's going to be red shifted. And that means that if we have an ensemble of atoms, all of which are along our pencil beam, those that are moving away are going to emit a red shifted photon. Those that are moving toward are going to emit a blue shifted photon. And those that are moving in some sense transversely are not going to emit a shifted photon at all. So if these motions Going back, now I hope you'll understand why that long digression. Going back to our discussion of an ideal gas, the photons that are absorbed are over a Gaussian range. The photons that are emitted are over a Gaussian range. And so the line profile is going to look like that. It's going to have a finite width, and it will have a more or less symmetric profile. And that is the whole basis of determining fundamental properties for any medium. The width of the line, in the simplest case, is given where these levels are really, really sharp. The width of the line is determined by the random motions in the gas. And the depth of the line depends on that phase function, that if for any reason the emission were isotropic, so let's say it would be sort of uniform in all directions, then that's different than if the emission is, as we had before, primarily a dipole. And it also depends on how broad these levels are. So every transition, this is something please to keep in mind. Every transition, if we had a cold gas, would have a different width. It would have a different wavelength. But all of them, if they're from the same medium, will be broadened by this same factor. And so this is usually called thermal broadening or the thermal profile. Now, that assumes, in the way I just drew it and talked about it, that the only reason these particles are moving relative to the photons that are coming in is because of thermal motion. That is, they're colliding, the medium is dense enough, or that somebody somehow has imposed a temperature on the medium. Now, that's not necessarily the case, or at any rate, it may not be the only reason. Take, for instance, the surface of the sun. It's convective. We have fluid motion in the gas, that's due to buoyancy, that's transferring energy from below to some region that we call the photosphere. And so you've got this bubbling of the surface. At one level, when you look at a photograph of the solar surface, and I hope you've all done that, you see something that is usually described as a bowl of rice. You see the granulation, the individual warm and cold regions. And you think to yourself, yeah, this is a kind of spotted surface. It's sort of irregular, but it's a little bit bright and it's a little bit dark. And that's it. And you kind of step back where we are, go to low resolution, and the only thing you would see is that there would be some averaging that would give you a kind of average temperature. But there's something much more important. That's the long way to the story. The short way is the reason it has that appearance is because just like soup on the stove, it's boiling. Okay, that's using a terrestrial kitchen term to describe something that is usually referred to as Archimedean instabilities or buoyancy. But what you call it isn't important. What is important is the medium is moving. Okay? You know that because if you look at the surface of soup when it's boiling on the stove or water, you see that there are parts that are rising and parts that are falling. In the granulation, the rising parts are brighter because they're porting energy up from below. They then cool, they emit, and they change their density relative to the background and sink. And so this is the simplest way of looking at it. You have upward and downward moving gas blobs. Now, on the surface of the star, each one of those has an intrinsic profile that may look like this. But because you have the part that's rising being hotter, literally hotter, brighter and hotter than the part that's sinking, they don't have the same spectrum. One of them, the hotter one, may have ions. It may have, for instance, lines of ionized iron. And the sinking part may have lines of neutral iron because of the temperature difference. So they literally are going to have different velocities relative to you. That the neutral lines, if you think about it, the ones that are sinking are going to be, as you said, red shifted. And the ones that are rising are going to be blue shifted. And so if you were to look in this extreme case from a simple moving medium, randomly moving, you're systematically going to see blue shifts on one and red shifts on the other. They may also have different intensities, simply because if we have a dark medium, it's dark. We're not seeing it. If we have a bright medium, we are seeing it. So we even have a bias that the rising part of the medium, of the surface, is brighter than the part that's sinking. Okay? We have to take that into account. And that's in the line profile. The broadening isn't simply a thermal broadening. It also is averaging over these macroscopic motions. So the broadening is not just thermal. It's because you're looking at a moving medium. It's a very slowly moving medium. Generally, it's much slower than the speed of sound. So it's much lower than the thermal broadening. But nonetheless, it's always there. And that's the first example of having to deal with line formation in a moving medium. That we may, when we're looking at some structure, simply see a broadening because every element in the structure is randomly physically displacing at velocities that are collective, like turbulence, like eddies in a stream, like boiling in a pot of water. This broadens the line beyond temperature. And so if you were to say that the width of the line was due to thermal broadening alone, you would get the wrong answer. You'd say the medium was too hot. But now we'll go back to something from a couple of weeks ago. The temperature determines which lines are present, their strength, and also even their presence in which ion the medium might have. If the temperatures are high, it may be ionized. If the temperature is low, high and low here being relative, it may be neutral. So you can have a gas that shows neutral sodium which practically ionizes if you look at it the wrong way. And in the same spectrum, you may have, ionized iron, which it doesn't take that much more energy. But when you look at the width of the line, instead of it being like equivalent of 10,000 degrees, it may be 50,000 degrees. Neither of those ions should be present if this were just thermal. And this is the origin of the second component in this argument. In the first, the thing that gave us this, we had just random motions, and those were thermal at the microscopic level. And so we call that temperature. Okay? Thermal broadening. Now, if every element here is actually blobs that are moving around macroscopically, as in turbulence, then that is going to give you a broadening of the line that is above the broadening that we would get from the thermal. So, step number 2. When you measure the full width, half maximum of a profile, you're making a very strong assumption that that is giving you information about either kinetics or kinematics or both. You are also assuming that you know what that width means. Because if we have a profile that's Gaussian, in other words, purely thermal broadening, you know that the width of the line gives you the temperature. And you know that thermal broadening for an ideal gas, we were all brought up saying it has a Maxwell-Boltzmann distribution and velocity. And yeah, this is just jargon. It's a bunch of Gaussians. It's random motion and random velocities. And consequently, we have an isotropic medium, and the random motions of the individual particles are thermal. If it's turbulence, if it's convection, although traditionally we use a Gaussian representation, you'll hit the word microturbulence in the literature. This is a wonderful expression of ignorance. We don't know what that stands for. We simply are saying that we don't have any reason to choose one form for the motion or the other, so we now have a random process that's giving us a Gaussian. And the width of that Gaussian doesn't give you the temperature. It's from something else. And that something else, because it's convenient, we call it turbulence. Now, virtually every star that we measure, when we have some indication of the temperature of the star, almost always gives lines that have been broadened by more than what should be the thermal width. And so this has given rise to the application when interpreting a line profile of microturbulence as something characteristic of an atmosphere or characteristic of a medium. In the interstellar medium, it's correct to say that we have random motions on very large scales relative to our line of sight, no matter where we look. The velocities, though, can be enormous. Tens of kilometers per second, sometimes even more than that. Something that can't possibly be thermal. But we also know that the general behavior of the structures we see aren't Gaussian. So it's just a way of keeping in mind what is now going to go to the next share. So let me go to a screen share again. And so now I hope with that long digression, and I hope you're still hanging in there. The distribution and angle, both coming in and going out, but this angle, this is actually the emission probability, is measured relative to some line of sight, just an arbitrary zero. So what we want to know is, in the re-emission process or in the absorption process, thermally, what would we expect? And then in random motion, there would also be, between the velocity vector, that is the direction of motion, and the line of sight, the physical motion, that also produces a different pattern. That, yeah, this is the pattern in the frame of the atom, but the observer could be anywhere in any of these angles. So if the atom happens to be moving to the right, this may be the direction, and the observer may be down here, and the shift in frequency will not be the same as if the observer is here. Okay? Putting that together, we get this down here. This is the line profile. So now we have the last step in the discussion before going to moving media and what that means. It's a new way for you to be thinking about the walk of a photon through a medium. If you're absorbed, the cross section tells you what the chance is that anywhere along the line of sight, you're going to see an opacity source. So if the photon happens, if when you're looking at light, you have a photon with a wavelength here, this is now in wavelengths, then miraculously, it just keeps going. That for all practical purposes, the probability of being absorbed is zero. And so we say that it has maximal escape, or that this is an optical depth that's negligible. On the other hand, the closer we are to the resonant frequency, the greater the cross-section. Never mind cross-section per unit atom, never mind per unit volume, cross-section. That a photon at this wavelength has a much higher probability of being absorbed. Okay? Now turn that around, because where you have a high probability of being absorbed, you also have a high probability of being emitted. And that's the key to understanding the last step here, that line profiles intrinsically are damned close to symmetric about line center. If you take the resonant frequency and you look at the wings of the line that result from the broadening of the levels, again, this is the intrinsic profile. If you absorb anywhere out here, it's still the re-emission, the photon that comes out of this system, eventually still has the highest probability of coming out at line center. Okay? That's the random walk. That if you've got a photon whose frequency is very close to the match, the resonance frequency, then its path is much shorter between successive interactions than the one that's coming from somewhere in the wings or even farther than the wings. So now there's a third factor that we have to include. So it's not just that the distance that you go is random, the distance you go is determined by your wavelength. And that closes this discussion in the sense that now we have all the ingredients. If you're at a resonance, your mean free path is going to be low. If you are absorbed, then you may come out at the same frequency. The likelihood is you will, but not the certainty. The line profile is a probability distribution in the same way that a Gaussian is a probability distribution. The most likely event is not a large displacement from line center. And that's why line profiles look the way they do. Most of the photons come out at that point where the cross-section is largest. Why this is important is that if you imagined having here a stratified medium, so now you have the photons coming in here. These are simply, actually, let's just imagine for the moment here that you have light in this direction we have frequency. Okay? And somewhere here there's an emitting surface. Light comes in incident on this medium. So the light at, let's say, 5,000 angstroms goes right through. This plane is completely transparent. But we've put a barrier here at, say, H beta. And so photons that are coming here see an obstacle. And for the moment, we'll say that they're absorbed. So we get an absorption line. That's A. Now, if the next if the next level, some distance delta L, some geometric distance in the medium, just chosen randomly. I know that when physicists say that, there's always going to be somebody who will hear that and think, that's crap. What do you mean by randomly? It means, in this case, it's not important metrically what that distance is. You just want to imagine two planes. Whatever's in between them, for the moment, we'll leave out. Now, if these two were static relative to each other, then these targets would line up in frequency. And so the more path you go through, the more absorption you're going to see. And so the line gets deeper. Okie doke? But if it's shifted, if this plane is moving relative to this one, then the photons, remember I said when they're re-emitted by the medium, they come out primarily at line center. But now line center from A is shifted from line center at B. And so those photons are going that were here out of the line suddenly find themselves being re-emitted and traveling into a line. The medium is darker than it should have been. And so we get the profile B. That is, we get a shift here in the absorption and a little bit more light comes out now than we would have seen otherwise. And if you put C in, you get even more light coming out at wavelengths that formerly had been opaque, and light being absorbed at wavelengths that formerly had been transparent. This is the P Cygni profile. This is light in a moving medium. What you've done is change the random walk step. So when you're looking at this, what's going to happen is that some photons are now going to go much farther than other photons. So the profile now depends on the local velocity of the medium. This is uniform. This is not random. And so the profiles are not broadened, they're shifted. The result is that you get both absorption and scattering when you're looking directly into the flow. And then depending on how much isn't obscured, you're going to get scattering. That all of this part, and you've seen this gazillion times when you look at the sun through clouds. In fact, bingo. Perfect example of having now not a moving medium, but a very specific one with very specific angular characteristics. This was over Prague a long time ago, when it just happened that there was a cloud deck with some ice in it. And that's the setting sun and sundogs. You not only get dispersion here, you also get them at very specific angles, which means that the light that was coming out from the sun here is scattered by a layer of ice, but also that light that's coming out this way is scattered into your line of sight. In this case, this works so easily, so beautifully, because it's all resolved. Now imagine that all of this is shrunk down to an unresolved object. If the medium is moving, then around this rim, you're going to have different velocities than in the stuff that's scattering closer to the sun. Another example is here, that this is a turbulent medium. This is, I could say this is Pisa on a really good day, but good meteorologically isn't good astronomically. But this is what I was talking about when saying we have turbulent motions, that each one of these is actually a rolling structure. So you have an ensemble of shearing layers here. If you look at light passing through this, it isn't simply that it's going to be more or less obscured depending on the density of the droplets. It's also that the medium here is moving with a bulk velocity relative to, say, down here. And so it isn't just that one is more transparent than the other, it's also that it has this dynamical signature on it. This is what I meant by scattering, that you have a light source somewhere embedded in this cloud, actually behind it. And there's a scattering medium. You have aerosol particles in the air. And the brightness here depends on how the light emerges from here and gets scattered into your line of sight. Okay? But this is turbulent. It, in fact, was very turbulent on that day. There was an impressive wind, like, 20 meters, 20 meters per hour, which is impressive actually for standing. And so the light here, every single line in the solar spectrum that was being scattered was being broadened. Now, the temperature of this photosphere, the broadening of the lines from photospheric motions, which instead of being meters per second are kilometers per second, is a hell of a lot higher. But you could imagine that here you have a star, and here you have the interstellar medium, and these are the structures that we would call interstellar clouds. And so when you're looking at the scattered light passing through those clouds, it's broadened. And it's broadened in a way that depends on the dynamics of the medium. Now, this could be, it's not, but it could be a plume, a jet that's rising. And that would be a systematic velocity field. And so here the scattering would indicate that you had an ordered kind of filamentary bulk motion. So you would be able to get information even if this all shrinks down to a point about the line of sight dynamical behavior of the medium. Now, this is an example. We used this a long time ago for talking about ejecta versus jets and so on, but the thing that's important is that when you have a moving medium, the difference between successive layers in velocity changes how much light is removed at every wavelength. And so rather than just talk about it, this is an example that I have to change screens, I think. So yes, here. So we'll start with yes, here. Wonderful. Why is that not? So window. Okay. Please pardon. Okay. So we'll say this is a spectrum. Now this is a synthetic spectrum. It's iron elements, iron and related elements in a gas. This is just a model, so don't get too excited. But if okay, these are the individual lines. So you could imagine that this is the surface of the atmosphere of the atmosphere of a star. And in this case, this is static. So if we increase the amount of gas along the line of sight, in other words, we make it denser, then the profile goes to that. And if we increase the density even more, the profile may go to that. Okay, so the individual lines are just getting deeper and deeper and deeper. And eventually, we might even get this, where everything is just absorbed out and only a few windows remain. One here is the surface flux. But in contrast, so if we go back to the original version, So there's our single line. Imagine now that we have a medium, we have a wind where the velocity increases as you go away from the star because it's accelerating, like the solar wind or any stellar wind we've talked about. The farther away you are, the lower your density is because you're spreading the material in mass loss if it's steady over a larger area. So part of it is that the lines are being blue shifted because it's moving toward you. And part of it is that each layer that has a different velocity has a different density. In other words, a photon that's emitted, say, if this is distance, a photon that leaves here may go this far before at that frequency it hits one mean free path. Okay? But then it may go farther on the next step on average because now the density is lower. And so even at the same frequency, it escapes. And at the next frequency, at the next step, it may leave completely. So, part number 4, always remember, photons are stupid. They go in straight lines until they hit something. And that's all you need to know. That when talking about the optical depth, and now I can finally use the term, the optical depth is just a measure of the mean free path. It determines the probability that something is going to happen, but it is not that probability. So when you talk about the mean, this random walk, the length of each step is is related to the chance that that step will be taken, and that is the line profile and the way the profile shifts its center. It is related to the optical depth. If the medium is moving, if one part has a velocity different than another, then light that comes out of one layer has an either increased or decreased chance of going the same distance as that which got it into that layer in the first place. That is the core idea of transfer in a moving medium. And to show that point, let me put up what happens if we have a wind and a density gradient. Okay? Steady wind. You see the profile now as it would be if it were steady. Okay? So far? You
Yeah.
can all nod yes. That's what happens if the medium is moving. Okay? That is, you've not only changed the absorption at line center, but you've also suddenly increased the absorption away from line center asymmetrically. This is an outward moving steady state wind. No gradient, just assuming that it's spherical outflow. Now, if you had a different density gradient, then, for example, if it changed more steeply, that's very dense on the inside and very, very low on the outside, you might see this. Or this. where here, actually, let me just do 4. You see that the line is very heavily weighted toward the inner part where the velocity is low. If you change that and weight it toward where the velocity is high, you get that. In other words, the line profile now, once you got a moving atmosphere or a moving envelope, reflects through the shape of the profile, the medium through which you're transferring the light and its dynamics.
Steve, this is the medium moving rapidly toward us, hence blue shifted.
Yes.
Got it.
And in this case, I'll be honest, I cheated and took this as an extremely simple velocity law, but also as just a bunch of slabs, all of which have the same spectrum. This is essentially what you'd get from it being isothermal. Sometimes hard to actually admit these things. Now, Francois had wanted that at some point we actually look at something real and not just these fakes. So here's a real line profile. This actually is an expanding ejection. It's T Pixidus, but that's not important. What is important here is this. This is H beta, for those of you who like to be introduced properly. And you see that the rest wavelength, now to put this in its proper form, that is, we plot this in velocity. So you would interpret this as saying that you have the bulk of the emission. If you look carefully, you can see that there's a sort of emitting profile here. It's not Gaussian, so forget that crap, but it does seem to have some kind of regular shape. And then there is absorption extending out to a couple of thousand kilometers per second. And structures, that is, individual absorption features within that. So the interpretation here would be that you've got some surface. The surface is what's producing this broad continuum of emission. This is the photosphere. Whether that photosphere is stationary or moving, you don't know, and you can't know, because what you're seeing here is simply where the light has been able to escape. And the medium is so low density that the only things that are absorbing are lines from something that we can call the ejecta, something away from the surface, or from a wind. It doesn't matter here. What does matter is that this, when we say it's an absorption, this is absorbing and scattering both. You don't know which one is responsible. You only know photons are being removed, and they're being removed from line radiation. That also is going to affect everything out here too. So the only reason we worry about photons traveling through a moving medium is because we're looking at line photons. If the medium is moving, continuum photons do not care. Okay? One is just like the other. There's no resonance frequency. So it doesn't broaden the line. There's no line to broaden. Now, another example was, let's see, here. Um, this is actually H beta in a disk in a binary system. But again, it's a moving medium because you can see already something is really bizarre, that the width of this line at zero intensity is 1,000 kilometers per second. The half width of this line at zero intensity is so wildly supersonic that you would never see hydrogen lines from something like that. And to make a stronger point, the line that I've just overplotted is here. So there's H beta. And that other line that I just overplotted, this is iron. It's iron 2, just as an example. And it's partly an emission and partly an absorption, and everything looks kind of like that same spectrum, but that if we look really hard, now we have lines that are broadened by dynamics, lines that are exceedingly sharp. This is not noise. These are lines from a photosphere. This is what we mean by thermal broadening, or thermal plus really modest convective motions. These emissions, which are all very strong, either iron lines, iron ion lines, or other heavy metals, all are coming from a region which is physically moving at hundreds of kilometers per second, and the rest of the medium is in dark lines, which are most likely, most likely due to scattering. Now, I want to do, so going back now to H beta. The way you will, now we can interpret this in another way. You see that these two peaks are asymmetric. Um, Now, there are two ways of looking at this. One is that you have the usual way of doing it. You have two components. One is blue shifted, one is red shifted, and the blue shifted one is weaker than the red shifted. Okay? And you might very well look at this and think that, okay, you have two separating components. Or you could say, wait a minute, this isn't at line center. That one thing that may be happening here, going back to the cartoon, if you remember it, of the outflow, is that this is from an absorber against this. And so you actually have a wind here being seen against an emitting region. In other words, like the sun over the bridge and scattering. Okay?
Yeah.
Now, with all of that in mind, because you've been so patient, uh, let's go back to the whiteboard for a minute. And now go to an exercise. This is something that may help you drill this stuff into your head. Take a spinner or dice. Um, Actually, I think having dice will work even better than the average spinner, but two dice work even better than one. Shake the dice and read off the number. So far, this sounds really technical, right? Um, Now say that you have just built a random number generator, which can produce a set of numbers between 1 and 12. Well, actually between 2 and 12. Say, for the hell of it, that those are angles between 2 units and 12 units relative to a circle. And so if you come up with, let's say, two ones, that means the next step will be straight right. If you come up with two sixes, that will not be in this direction. You could, in fact, say, oh, that's exactly in the opposite direction. And then take anything here from 0 to 180 to be any number from 2 to 12 inclusive. Okay? That is what would be an isotropic process that if it comes out at any of these angles, the next is going to be leaving in that direction. Okay? Now, having done that, the next step is, okay, you know that a scattering has occurred here. What is going to be the distance to the next scatterer? In other words, along this direction, how far are you going to go? Remember, I said that this distance will always be as far as the photon can go, but that's a deterministic way of saying it. And instead, the actual probability that the photon is going to escape, is this, that this is the optical depth, which is actually the path length. So what you'll do, God, I hate doing this with a mouse, is say, well, This is what I had drawn on your other slide. You have a random number here that goes between some minimum and some maximum. So let's say this goes between actually 0 and 10, okay? So just subtract 2. That way, this becomes 1, this becomes 0. Now, that means that the probability of escape is 100% if the optical depth is 0. That's called a vacuum. So the escape probability is 1 minus the absorption probability. And if you look at that cumulant, you get this. That is, this will be optical depth infinity, or L equals 0. This will be anything less than infinity and greater than 0. And so if this is a random number, which means your dice, throwing the dice and getting, let's say, 12, which means 10, highly improbable, but that means that the photon will go a distance like this. Throwing a 5, the photon will go a distance like this. Throwing a 1, it may go a distance like this. And so now you have two numbers. First, the angle that it goes off at, and then how far it goes. Then at the next scattering, it may go in this direction by this distance. And then in the next scattering, this, and then the next, this, and then the next, this. The exercise is look then at here the distribution of where these photons are landing relative to the ones that are going straight ahead. Okay? The reason for doing this is to give you a feel for something you can then look at in the sky, namely those clouds that I was showing you. And then you can imagine what this does to a line profile. That is, this optical depth, this tau, is the absorption cross-section times the column density, which is the number of absorbers or scatterers along the line of sight, which is usually just called N. So if you have the lines shifted, that this is, sorry, that this is the profile from one depth, and this is the absorption from a layer above it, then a photon that emerges here goes straight out. And a photon that emerges here gets trapped. And so the profile you see will look like this. The process I just described, I'm afraid poorly, is called the Monte Carlo method. It was invented during the Second World War at Los Alamos for calculating how neutrons are transferred in a nuclear pile. It's a way of doing transfer of any body. Um, it was based on this idea of a random walk. The reason for going through all of this is that when you measure a line profile, this is a way of understanding what you're looking at. So to now stop sharing. When we look at stellar spectra, because those are the easiest ones to deal with, stars having a hell of a lot of gas between their outer layers and where their nuclear fuel is being burned, have so many scatterings, so many interactions, that the interior can be thought of as an opaque blob with a surface. And then, because they're gaseous, that surface is only apparent. Where the opacity is large, the star looks big. Where the opacity is small, you see deeper. And that's the idea here, that when you have this random walk, it isn't only in direction, because it depends on the opacity, it depends on the line profile. That changes both because of the ambient conditions of density and temperature, but also because you may have a moving medium, and you can then distinguish those. If you have a wind, winds start slow and end fast. They accelerate outward like the air blowing out the back of a vacuum cleaner, where if you have ejecta, it's closer to something more antisocial, like passing wind or an explosion, that everything may be blowing out at almost the same velocity. All of the fragments, if you imagine a perfect explosion, would simply be going out radially, and the only thing different between them would be their velocity relative to you. In reality, you know that when you have explosions, some stuff goes faster, some stuff goes slower, and along any line of sight, the fast stuff and the slow stuff may be along the same line of sight. They maybe even be cospatial because one is running through the other. All of that imprints on the line profile. And once you do this little exercise of the random walk with the dice, I think you'll be able to generalize in your head what happens when you let a photon decide which way it's going to go. That the process of understanding what a spectrum is telling you is fundamentally thinking like a photon. And this is the closest way I know to getting into that mindset. The interaction of light with matter imprints on the light that makes it through the properties of the matter. But those properties are not only as we learn in childhood, and this was where we started this discussion. It is not only the composition of the medium, it's not only the temperature of the medium, it's also the dynamics of the medium. This is what a P Cygni profile is. This is the way you interpret it. This is what emission and absorption superposed in the same spectrum means. This is what happens when you have multiple clouds along the line of sight, and each one of them gives you an absorption feature. All of that, really, you can understand with this little exercise. The, um, the last example of which, because it's clearly taxing you. If you have light being transmitted through a cloud, and that cloud could be cosmological, it could be clouds along the line of sight to a cluster of galaxies, or it could be individual clouds in the Earth's atmosphere. Each one of these blobs will leave an imprint where this is wavelength or velocity, and this is the amount of light that's been removed. And from different directions, this is going to be different. So the reason for giving you that exercise with the dice is that every one of you, if you do it, will get a different answer. But you'll see the sensitivity to it. What happens if you change the opacity of the medium? So you put something in that's intrinsically very efficient in absorbing. Then obviously all of the paths are going to be much shorter, and you're going to get much more light removed from your line of sight, because the probability that it's going to keep going in the same direction becomes progressively smaller the more scatterings occur. Okay? Absorption or scattering can be then put into the same thing, the same process, and so you can conceptualize how the light will be transferred through this, or how the light would be transferred if you happen to see it on the side. Okay? That geometrically, just one last point, if you have a sphere, everything's really simple. If you have a slab, everything's simple. This would be, let's say, a jet. Then the material that's flowing this way is potentially going to have the same optical depth as the material flowing this way. Okay, you're at the same distance from the center. But here, if a photon is emitted, let's say here, where my pointer is, if it goes out this way, it escapes. If it goes out this way, it doesn't. If it goes out this way, on the other hand, if this is expanding like a jet, if it goes out this way, it sees something that looks static. So even though it could go farther, the opacity in the line is stronger here than here, because this may be shearing, and so reduced by the fact that you're shifting the line, as we just did. Now, I'll finish here because you've been incredibly patient. And I apologize that this has been so technical, but this is really what the world is when you're doing astrophysics. This is how you pass from those wonderful observations of spectra to actually dragging out of them all the information you possibly can. This is how you reason about this. This is not how you model it, because every process I've talked about, you can discuss without placing it in a particular context. This is what it means to do radiative transfer and spectrum formation without doing phenomenology. You first understand what the imprints are on a spectrum, and then you can begin looking for the clues. That is, which of these do you see? The signal of scattering, the signal of magnetic fields, of turbulent broadening, of pressure broadening, of outflow, accretion, or circulation. Every one of those leaves a mark independent of the combined details, and allow you to go backward to deduce from the evidence the physical state of the medium, instead of starting with a model for it and then just fitting parameters. It's a way of appreciating the varieties in nature just from the spectrum. And the other, and I hope motivating and last point, is that if you let yourself ruminate on what we've been discussing today, you'll realize that you can actually do this in your head. You can actually see this without imposing models or imagining the images that are generated by computer. This is actually a way of visualizing the cosmos and consequently entering it. And so on that note, let's end and throw it open. if there are any questions, if there's anyone left standing.
I'm still sitting. See, this is Wayne Green. I go back to the early Big Bang universe when the gas was only hydrogen, helium, and a smidge of maybe lithium or something.
Yeah,
And we look at a core, and a core starts collapsing. And as the collapse takes place, thermal excitation takes place, photons are emitted.
yeah,
But there's a velocity gradient across that collapse. So I really don't have any line support for material to stop material from inrushing. And I wind up with a super huge initial star,
hmm,
doesn't live very long. It novas and does its tricks and produces this multitude of objects. And in the process, pollutes the interstellar medium
yes,
so that the second generation stars that come along, now they have more stuff. And now we have the same velocity gradient,
you
but we
got it.
have a higher probability of an element absorbing a photon
Yes.
and reacting to it. So I can't have the big stars I had in the early Big Bang universe.
This is a part of it, yes, that if that particular form of radiation pressure is involved, you got it.
And
That
that's essentially a line through this lecture this evening, correct?
it's part of it.
Yeah.
That,
Yeah. There's more to
but
what
this
you were
is
saying in the
the other
fluid
way. No, but you
environment.
can go the other way around. That um, if you have only electrons, and remember, electrons scatter.
Yes.
Okay, and in the same way that when you're playing at bowling or no billiards, that the ball is actually hopefully it's not fusing, that it's scattering off the other balls. Uh, you you even if you have electrons, because they're charged, they react to electromagnetic radiation. And so if you've got a stream of photons, the scattering of the photons is going to give you a kick. That's the
Mhm.
absolute minimum cross section you can have. And so if you're going to drive outflow, which is what will happen if you've got enough flux, that it actually has radiation pressure that counteracts the effect of self-gravity. That in the early universe, you also had very inefficient winds. So you could, in principle, build much more massive objects because they were limited only by radiation pressure, mainly on electrons. That uh, hydrogen atoms are really lousy scatterers. Uh, for one thing, they require an enormous energy, that like 10 volts, before you can get line scattering. Now, on the other hand, in the next generations, as you said, you have metals. And metals are like that spectrum I was showing where I was putting on a wind and shifting the lines. The more metals you have, the more heavy elements you have, and the more electrons those individual atoms have, the more energy levels there are, the more transitions there are, the closer they are, and the more opaque the medium is. It also means that it cools differently. It means that you see it differently. The internal structure of the first stars was one that had very, very low opacity. So these could very easily radiate from their surfaces. They would appear very hot relative to those that we see with much higher metallicity, like now. That
Mhm.
would be the same mass, but more light from the UV would be blocked, and more light would have to come out in the visible. So yes, all of that is an effect. The opacity driving winds is the opposite of the opacity impeding accretion.
Mhm. Well,
This is
the other,
why this is the hard part of doing stellar cosmology. And this is what we don't really this is what we don't understand very well. We're still not at the point of getting the accretion and wind down. And it's a nice open question.
well, another interesting example I've come across is my good old friend, the Bubble Nebula, where a bright star wandered into a tenuous gas and blew a bubble.
Hmm.
And essentially, And to me, that goes to show, the effect of essentially line-driven winds. And you get compression, you get a temperature
Oh, sure.
gradient, you
You get
get
the
all
compression,
manner of things.
well, remember, you get the compression because the velocity with which the wind is leaving the star, because it's leaving the star, is supersonic, necessarily. And consequently, it's going to be higher than any sound speed in the external medium. So it doesn't matter if the star is in a low density region or not. It's in the interstellar medium. It will always have a peripheral region for a wind, no matter what that peripheral region looks like. Okay? Uh,
Mhm.
when you see the nebula, that's because the star itself is hot enough to ionize the gas. But all stars carve out cavities. The sun is sitting in its own cavity. It's called the heliosphere.
Mhm.
But we wouldn't see that if we looked from Alpha Centauri toward the sun. We wouldn't see the heliosphere because the densities are just too low and the sun doesn't produce the ionization of that medium. But if the sun were instead like, oh, Spica, which is a B star, then it might have enough photons that it could actually ionize that medium. And so you'd actually see the glowing recombination from the region that had the compression, that had the higher density. When you're looking at a Wolf-Rayet star, the reason you have these bubbles is that the wind is going as far as it can, that it's pushing and coming and stalling at this background. It's continuing to expand,
Mhm.
but extremely slowly relative to the velocity with which it's leaving the star. But the central star has so much UV that that region is ionized, and that's why you see it.
Mhm.
The same thing with planetary nebulae, that the wind coming out of the central star is what you call the nebula. That is, it's the low density stuff that's being ionized. But outside of that is the old wind from the asymptotic giant branch star, from the star in its red supergiant phase. And that is being pushed on, but all of the ultraviolet has been absorbed in the inner part. So
Mhm.
you don't see that. What you see in that is what JWST sees. You look in the infrared and you see the hot dust, but the bubble that you would see in the visible, that's the emission lines that are coming from the ionization from the central star. And that's
Can't
the
get
same
away from
thing.
it.
You see that also in active galaxies. I mean,
Yeah.
that's the narrow line region of an active galaxy.
Thanks, Steve.
Those are wonderful examples. Thank you.
Other questions for Steve? No, it's late. I